So friends, we were discussing about the factors that can affect the extraction efficiency in a microwave assisted extraction technique, and in that we were discussing about the solvents. So apart from using good microwave absorbing solvent or a mixture of high dielectric loss and a low dielectric loss solvent, that is methanol and water, I have taken an example, or you can also use a microwave transparent solvent to extract out volatile constituent from the fresh drugs because of the presence of moisture in those fresh drugs. And the third type of solvent which one can use are the alternative solvents, and one such example of alternative solvent is the ionic liquids, which have been gaining importance or interest in the recent past. Now these ionic liquids are nothing but these are composed of organic cations and inorganic or the organic anions. So they both have they have both cations and anions, and more importantly they are liquid at room temperature. Therefore such kind of ionic liquids are becoming solvent of choice for extracting different types of constituents. Now apart from these properties, they have certain other excellent properties that make them solvent of choice, like they have negligible vapor pressure, because we know that whenever you are exposing a mixture towards microwave irradiation, then that tend to heat up and it will cause certain evaporation of the solvent, thereby increasing the vapor pressure. So high volatility of a solvent will always have high vapor pressure, but these solvents are I will say not much volatile or non-volatile, therefore they have low vapor pressure. They have good thermal stability. They have tunable viscosity. Now tunable viscosity is important because we know lower the viscosity, better the penetration, more will be the solubility. So depending upon the requirement of the user, one can always tune the viscosity of ionic liquids by changing the cationic or the anionic groups present in the liquid. And because of their variability of their composition, they have miscibility both in water as well as the organic solvents. And not only they are soluble in water and organic solvent, they have good solubility and extractability of various organic compounds because of their varied chemical nature. The next factor that can affect the extraction efficiency is solvent to feed ratio or solvent to drug ratio. In general, if we see, the solvent volume should be must or sufficient enough to completely immerse the sample from which we want to extract out the desired constituents. Why is it so? Because it has been found that such kind of immersion help in better swelling of the matrix, and when the matrix swells, it lead to the better extraction. Normally it has been found that solvent to feed ratio of 10:1 or 50:1 is frequently used in the microwave assisted extraction. But again, the ratio which you want to use has to be optimized for each raw material, because every raw material has its own characteristic properties, and therefore the solvent to feed ratio has to be optimized depending upon the nature of the raw material, whether the raw material is soft, it is hard, or it is moderately hard, because hard material requires more solvent because they have to penetrate through a hard matrix, whereas softer materials, they require lesser volume of the solvent in comparison to the volume of the drug. Now whenever we have to optimize this solvent to feed ratio, there can be two scenarios. First is we can keep the solid or the matrix mass constant and we can vary the solvent volume. And the second scenario can be we can keep the solvent volume constant and we can change the solid or the matrix mass. Each scenario has its own effects. So coming on to the first scenario, wherein we keep the solid matrix or the matrix mass constant and we vary the solvent volume. And it has been found that the yield normally increases with the increase in the solvent volume, but up to an extent, and then it start decreasing or there is a insignificant increase in the yield. And this is because as you increase the volume of the solvent, there is non-uniform distribution of the microwaves, because to accommodate that increased volume you have to select a larger extraction vessel, and when you select the larger extraction vessel, obviously the distribution sometimes become non-homogeneous. Further, when you use large volume of the solvent, larger extraction vessel, the stirring mechanism that was designed for that microwave extractor becomes inadequate, and this is also the reason why there is non-homogeneous distribution of the microwaves. Now, excess of solvent sometimes lead to excessive swelling of the plant material, and this excessive swelling, though the swelling of the plant material helps in better extraction, but excessive swelling of the plant material sometimes cause non-homogeneous distribution of the microwaves, thereby decreasing the extraction efficiency. Now, the increase in solvent volume also causes, as we discussed, increase in the extraction time, because more time will be required to heat up that solvent. And since more time is required to heat up the solvent, high energy usage is there, not only to heat up the solvent but also to concentrate the solvent once the extraction is complete. Further, with the increased solvent volume, it has also been observed that the selectivity of the solvent decreases. So, if a solvent is able to target the desirable constituent at a particular volume, and if the volume is doubled, then it tends to solubilize other unwanted constituents also because of the co-solvency principle, which becomes more effective when the volume of the solvent is increased. Now, we move on to the second scenario, that is where we keep the solvent volume constant. And in many cases, it has been found that with the increased solid loading, that is when you increase the amount of the matrix, the yield normally decreases. This is because as you increase the solid mass, the per unit surface area for per unit volume, it also reduces. Say for example, you were extracting 100 gram of drug with 1 liter of the solvent, and you increases the solid mass to say 200 or 300 gram, and now this 300 gram is to be extracted with the same 1 liter of the solvent. Earlier, the number of the molecules of the solvent that were able to penetrate the solid matrix in 100 gram will now decrease because you have increased the solid mass. So now say in the previous case, say 5 molecules were able to penetrate into the drug particle. Now you tripled the solid mass to 300 gram. So the number of the solvent molecules may reduce to 2 or 3 because they have to cater the increased solid mass. So this is how it affects negatively the overall extraction efficiency. Microwave energy is absorbed and dispersed by the larger amount of the plant material. So more amount of the energy will be absorbed because we have increased the solid mass, and it will be dispersed by the larger amount, which sometimes causes a non-homogeneous distribution of the microwaves. Now the incident microwave radiation per particle decreases with the increase in the solid loading. So this is the same as the case of the solvent molecules that were to penetrate into a solid matrix, and this decrease in the radiation per particle, it causes the decreased microwave assisted extraction efficiency, and it causes the low dielectric heating, thereby reducing the effect of microwave radiation, because now the per particle microwave is decreasing. Now absorption by microwave radiation by the plant material near the surface of the vessel reduces, and the penetration depth of the microwave radiation into the suspension. So since you increase the solid load or increase the matrix amount, this matrix amount which is near the surface of the vessels, it causes reduction in the penetration depth of the radiation. And as the penetration depth reduces, the overall heating effect also reduces, and this has a negative impact on the overall extraction efficiency. Now we move on to the factors of temperature and pressure. We know that as you increase the temperature, there is a decrease in the surface tension. Decrease in the surface tension will improve the wetting of the plant matrix by the solvent. It's not only the surface tension that is decreased, but it also decreases the viscosity of the sample. And as we discussed, that lower the viscosity, better is the penetration. Better is the penetration, higher is the extraction yield. Further increase in temperature also causes the intermolecular interactions with the solvent, which tends to decrease. And when the intermolecular interaction between the solvent particles decrease, there is high movement of those molecules, or high molecular motion is there. And this increased molecular motion also helps in increasing the solubility of the components that are present in the plant cells. Heating of the solvent in microwave assisted extraction largely depends upon the ability of that solvent to absorb the microwaves. So again, the role of the dielectric constant also plays an important role. So if the temperature is if you want to increase the temperature of the reaction, obviously you have to use certain solvents which have good absorbing as well as dissipating properties. In the closed vessels, it has been observed that solvent can be heated above its boiling point, because the closed vessels are normally considered as the pressure assisted microwave extraction, because you can increase the pressure above the atmospheric pressure, and such increase in pressure helps in keeping the solvent into liquid form above its boiling point, and this also helps in the improving the extraction efficiency. Now again, the increase in temperature has to be optimized, because extraction yield will increase with the increase in temperature, but up to a certain extent, and if you increase that temperature beyond that point, the yield decreases. It can be due to degradation of the solute molecules at that particular temperature, and also excess increase in temperature causes the loss of the selectivity of the solvents, and therefore percentage yield of the desirable constituent decreases. Therefore, it is always advisable, depending upon the type of the nature of the plant material, depending upon the type of constituent you want to extract, one has to optimize the temperature and the pressure conditions. Next factor is the power of the microwaves. Now, like other factors, power also has to be optimized, because when you increase the power of the microwaves, obviously the overall extraction time decreases. But again, it has been observed that if you increase the time of the extraction along with the power, then it has minimal effect on the overall yield. I have taken an example of extraction of flavonoids, which I will discuss ahead. So increase in power and has to be optimized along with the time of extraction. Now, better yield with high power, you get a better yield with high power, but the time duration should be less. So extraction duration should be less. So this can be explained with the help of this example, wherein flavonoids were extracted from the roots of astragalus, and the extraction was carried out at different powers ranging from 200 to 1000 watts. And it was observed when the extraction time was 5 minutes to 10 minutes, there was a significant increase in the yield of flavonoids with the increase in power. But when the extraction time was increased to 15 minutes, which is indicated by the topmost line, you can see that when the extraction time was increased to 15 minutes, there was insignificant increase in the yield of the flavonoids with the increase in power. So bottom line is, one always have to optimize the power along with the extraction time of the process. And it has been found that the maximum power ranges between 600 watt to 1000 watt for the closed systems, because they have certain pressure limitations also, and it is around 250 watts for the open systems. The next factor is extraction time and cycles. Now, it has been found that increase in the time increases the yield, but again prolonged extraction times may cause decrease in the yield, probably due to the degradation of the constituent, because you are exposing the constituent to the extraction conditions for longer duration. You are allowing the constituent to remain in contact with the solvent for longer duration. You are exposing the constituent for longer duration to the elevated temperatures, and such conditions sometimes cause degradation of those constituents, which will decrease the overall yield. Further, increase in extraction time or the cycles of extraction has also effect on the selectivity of the solvent, because as you allow the plant matrix to remain in contact with the solvent at elevated temperature for longer duration, the selectivity of the extraction decreases. And as I told you, as the selectivity decreases, different other constituents which are not required in the extract, they are also extracted, and therefore the overall percentage yield of the desired constituent vis-a-vis to the overall extract yield decreases. And there are certain cases where you require longer durations for the extraction. So if you are under such scenario, then it is always advisable to go for multi-step extraction. It means you can divide your material into shorter extraction cycles, or you can increase the number of cycles to have a positive effect on the extraction efficiency rather than having a negative effect. It has also been found that increase in extraction cycles with the used solvent have not much effect on the yield. When we talk about used solvent, it means you are extracting the drug with the same solvent that was used in the previous cycle, that has been used in the previous cycle, because over the period of time it will cause the saturation of the solvent, which sometimes cause decrease in the yield, or it will not have significant effect on the increase in the yield as you increase the cycles, because the solvent gets saturated. It hardly matters you increase the number of cycles, the yield will remain almost same. But yes, if you are changing the solvent, you are exposing the material with the fresh solvent, then obviously increase in the number of cycles will have a positive impact on the extraction yield. Next factor is the matrix nature. And when we talk about the nature of the matrix, moisture that is present in the matrix becomes important in case of microwave assisted extraction, because as we discussed, water leads to superheating effect. Because of its higher dielectric constant, it can absorb large amount of microwaves, but because of its lower dielectric loss, lower dissipating factor, it can retain, it is not able to dissipate heat to the surroundings. Therefore, heat is normally enclosed in the matrix, which causes its superheating. And if moisture is present in the particle, it gets superheated. There is an increase in the pressure in the cell, which causes rupturing of the cell walls, thereby releasing the constituent into the solvents. Therefore, it is sometimes always advisable to expose the dry material to certain amount of moisture by soaking the dry material into suitable volume of the water, because it will cause swelling. Water will be immediately absorbed by the dry material, and it will increase, or it will cause the swelling of the matrix. So we will have two benefits. One is superheating of the particles, whereas swelling also increases the extraction yield, which we have discussed previously. So sufficient moisture in the sample and solvent with low dielectric constant can be used. This was the case which we discussed in case of microwave transparent solvents. So if you want to extract out volatile constituents, you can have sufficient amount of moisture in the sample. This moisture will heat up the particles, cause rupturing of the constituent, and you have used the microwave transparent solvent, which will remain cool on the outer side. So those volatile constituent will released into a cooler solvent, thereby preventing their evaporation, preventing their thermo degradation. So this can also be done. Next factor in the matrix is the particle size, and it has been found that the particle size ranging from 1000 micrometers to 2 millimeters is appropriate. Lower particle size increases the surface area, it increases the diffusion out of the solutes and improve the overall extraction efficiency. But sometimes excess low particle size cause agglomeration of those particles, thereby causing non-homogeneous distribution of the microwaves, which sometimes have a detrimental effect on the extraction efficiency. Last but not the least factor is the stirring. And as we discussed, stirring helps in maintaining the homogeneous distribution of the microwaves. Therefore, it can be related with the better extraction efficiency. Stirring also helps in improving the mass transfer process, and therefore extraction efficiency. Further, stirring or agitation, it helps in enhancing the desorption and dissolution of the active components which are bound to the sample matrix, this causing the overall increase in the extraction efficiency. Now we move on to certain modifications of the microwave assisted extraction. So first modification is the compressed air microwave distillation, and this was proposed in 1989 by Cravero and his group. Now this was the technique that was the first microwave, I will say, technique that was recognized for the extraction of essential oils from the aromatic plants and species. So as you can see in the diagram, it is mainly composed of three major parts. On the left side is the compressor. Central portion represents the microwave cavity containing the plant material, and we have a cooling system or the refrigerant system. So with the help of air compressor, the air is pumped into the microwave or into the extraction vessel which is having the plant matrix, and the sample is irradiated with the microwaves, thereby releasing the volatile constituents. And these volatile constituents, because compressed air is there, they will move towards the low pressure zone, so they will move towards the refrigerant system where they are condensed. And since these plant material will contain small amount of moisture, so water and volatile constituents are condensed in the refrigerant system, and since both are immiscible, you can always separate out the volatile oil or the constituent that are obtained from the plant. Second modification is microwave hydrodistillation, and this equipment is based on the classical principle of the hydrodistillation, but heating aspect is carried out with the help of a microwave. So you can see in the diagram that the microwave cavity contains the extraction vessel, placed in the cavity contains the drug material along with water, and this mixture is irradiated with the microwaves, causing heating of the volatile constituent, heating of the water, and both the water vapors and the volatile oil, they move towards the cooling system where they are cooled, and water is circulated back into the extraction chamber. And this is how you can separate the volatile oil from the plant matrix. Third extraction modification is the in situ microwave assisted extraction, and this was discovered in 2006 by Flemini and his group. Now what they did was they introduced microwave producer into the extraction vessel. So as you can see in the diagram, they introduce insulated microwave coaxial antenna inside the glass flask, which causes the heating, and this type of heating was found to be more effective than the irradiation of the microwaves. But the major disadvantage was the scale up of such type of in situ microwave assisted extraction is very difficult, because you need larger antenna, larger flask, and again you have to optimize lot many of the parameters. So the major advantages of in situ method was safe and versatile, because the antenna is itself inserted into the extraction vessel. Lesser time is required because now the solvent and the matrix are in direct contact with the microwave antenna, and it leads to lower extraction time and high energy saving, and it has also been found for the industrial application, but yes, scale up problems are there in this technique. Next modification is the microwave steam distillation, and this was developed by Chimet and his group in 2008, and this is somewhat similar to that of steam distillation of the volatile oil containing drug. Now the drug is placed in an extraction vessel over a perforated plate, and this extraction vessel is placed in the microwave cavity. Now from outside, the steam with the help of steam generator is passed into the extraction vessel, and this steam passes through the drug, thereby causing evaporation of the volatile constituent, and the mixture of the volatile constituent vapors and as well as water vapors passes on to the condenser, where both these are condensed, and since both are immiscible, we can always separate essential oil, which forms the layer above the water, being lighter than the water. So this is nothing but a modification of simple steam distillation with the help of microwave. Now if we compare the microwave steam distillation with the conventional steam distillation, you can see there is significant decrease in the extraction time. The orange bars shows the parameters of microwave assisted steam distillation, and blue bars represent the conventional steam distillation. So you can see there is a significant decrease in the overall extraction time. There is a significant decrease in the power consumptions when we go for steam distillation with microwaves. Then carbon dioxide emissions are also reduced because we are having two factors simultaneously acting, steam and also microwave radiations. So both these factors improve the overall extraction efficiency in lesser time, lesser power consumption. These are considered as greener techniques. You can see by the data of carbon dioxide emission, and the water that is being used is also very less in comparison to the conventional steam distillation. Next modification is the microwave hydrodiffusion and gravity. Now this is just the opposite of the distillation techniques which we have seen. Here the sample is placed above the cooling system, and as you can see in the diagram, the drug material is exposed to the microwave radiations, and by virtue of gravity, the vapors and the water vapors and the volatile vapors, they move towards the condenser, which is below the extraction chamber, and they get condensed. So again, such type of extraction technique, they do not require any kind of solvent. They just use the water that is present in the matrix, and therefore these techniques sometimes are also known as solvent-free microwave extraction techniques. Another modification is the vacuum microwave hydrodistillation. Now this was developed in 1990s in France, and this technique largely uses the vacuum to decrease the boiling point of the volatile constituents. Another technique is the microwave assisted soxalate extraction. Now microwave, this is not a modification, I will say it's a hyphenation, because we are mixing the two extraction technique like soxalate extraction with the microwaves. Now as we discussed in the focused assessed microwave extraction, sometimes soxalate extraction is also known as focused microwave assisted extraction because they use monomodal cavities. And extraction vessels are normally open in soxalate assisted microwave extraction, and therefore they work at the normal or the atmospheric pressure. Now extraction step is totally or partially performed as in the conventional technique in case of soxalate extraction, because in soxalate we know that there is a complete cycling of the solvent every time the drug is exposed to the fresh solvent. The heating part is carried out with the help of microwave, and that heating part is only localized where solvent is present, and therefore this helps in improving the overall extraction efficiency. And in this you can see the diagram of focused microwave assisted soxalate extraction, because they are carried out at atmospheric pressure. The microwave irradiation are focused to the extraction chamber of the soxalate, and solvent is evaporated from the heating mantle, but the solvent is being irradiated with the microwaves, thereby increasing the overall extraction efficiency, decreasing the overall extraction time. So this is the difference between the sox wave and focused microwave assisted solvent extraction. Then we have ultrasound microwave assisted extraction, wherein ultrasound as well as microwave, they are combined. This is again a hyphenation. Ultrasonic probe is inserted in the extraction vessel, and both ultrasonic waves with the help of cavitation, the microjet bubbles, when they explode, they rupture the cells. The microwave radiations, they will help in heating up the solvent, thereby increasing the overall extraction process whenever the drug is exposed to ultrasonic microwave assisted extraction. Now the last aspect is the application, and microwave assisted extraction helps in extracting out various kind of secondary metabolites like polysaccharides, lipids, essential oils, flavonoids and polyphenolics. They are largely used in food and nutraceutical industry for extracting out various food colors, various food additives, antioxidant nutrient constituents, to extract out proteins, amino acids. They also help in fastening up the chemical reactions, and microwaves are nowadays also used in omic technologies like proteomics, metabolomics, and genomics, wherein they are used for the sample preparation, they are used in protein digestion, and they are used as heat source in PCRs, that is polymerase chain reactions. So friends, this was all about microwave assisted extraction. Thank you.